Large language models operate without a human sense of reasoning or intent. They do not understand the underlying concepts of a prompt, they compute them. When a user enters the question, "What is the capital of Vietnam?" and hits enter, the software treats the characters as raw data points for a specific type of calculation. That keystroke triggers a deterministic mathematical pipeline, shattering the text into a numeric stream that flows through 96 sequential processing blocks. It manages 175 billion preset parameters, a fixed vocabulary of 50,000 terms, filtering queries through a multi-layered hierarchy. To see how these systems actually function, we must trace the step-by-step data flow of a single query, from the initial input to the final statistical prediction. At step 1, the system performs tokenization. It chops the raw text string into independent fragments called tokens, handling language as discrete units. Tokens are compared against a vocabulary dictionary. The model assigns each fragment a numerical ID, translating text into matrix algebra. These IDs act as indexed coordinates, navigating a massive data table to extract a horizontal row of 12,288 numbers. This 12,288-dimensional vector serves as the semantic coordinate for the word. It defines the token's relationship to every other word in the model's mathematical space. Transformers process data in parallel, so the model cannot inherently distinguish sentence structure. Positional encoding solves this by mathematically adding a positional matrix to the vector, locking the word into its specific place in the sequence. The text is now a dynamic 12,288-dimensional contextual matrix, prepared for the core processing engine. In step 2, the model focuses on the final token, the question mark. Because the model is causal, it masks all future data and uses this final point to calculate what is most likely to follow. The system multiplies the input vector by 3 weight matrices, splitting the data into 3 parallel functional branches: query, key, and value. The query represents the information the current word needs. The key acts as an identification tag for all preceding words, and the value holds the actual semantic meaning to be extracted and preserved. Multi-head attention divides the dimensions into 96 smaller subspaces, calculating different logical relationships simultaneously. The final token's query multiplies by the keys of previous words. Where vectors align geometrically, high similarity scores are generated. These raw scores are divided by the square root of 128 and passed through a softmax function, which compresses the values into a clean distribution of percentages between 0 and 100. These attention weights act as a filter. They dictate precisely how much of each previous word's value should be blended into the final token to provide it with context. After the context is established, the 96 independent attention heads are concatenated. This reunites the subspaces into the original 12,288-dimensional matrix size. This matrix then enters a feed-forward layer, where it expands to 4 times its original size, reaching 49,152 dimensions, before being filtered and compressed back down. This expansion applies nonlinear mathematical filters, isolating signals from noise. Finally, a residual shortcut adds the unprocessed vector back into this new data, ensuring the base definition of the word remains intact. By adding the original data back in, the transformer block can focus exclusively on layering new contextual updates on top of the established meaning. At step 3, the data enters a sequence. The output from the first block immediately becomes the input for the second, moving through a chain of 96 identical transformer blocks. The data evolves as it moves through these layers. Early blocks manage surface grammar, middle blocks deduce logic, and the final layers forge abstract representations. Recalculating every key and value for every word at every layer would stall the hardware. To maintain speed, the system uses an engineering optimization called the KV cache. The model offloads the calculated key and value matrices of all previous tokens into VRAM, storing them for immediate access in future cycles. Because the past context is stored, the model only needs to calculate the query, key, and value for the most recent token in the window. This optimization prevents the system from reprocessing the entire prompt with every new word, allowing for the near-instant generation of text. By step 4, the data has passed all 96 blocks. The final vector exits the last transformer layer as a highly refined representation of context. A reverse projection matrix multiplies this vector against a grid that expands it to match the vocabulary size of 50,257. This collision produces a sprawling array of output scores. These scores, called logits, represent the model's mathematical confidence level. A final softmax sweep converts them into a probability distribution, where the word "the" spikes as the most likely candidate. The sampling algorithm then selects the token with the highest probability and pushes it to the user's interface. Through billions of localized calculations, the model completes its task. It predicts the single token that is statistically most likely to follow the prompt. Step 5 expands this single prediction into a full response. Predicting the word "the" is just the start of a recursive cycle. This is the autoregressive loop. The new token, "the," is appended to the end of the original question, extending the context window by one position. Adding this token shifts the mathematical state, triggering the pipeline to restart. During this restart, the KV cache allows the system to bypass the original prompt. The model only calculates the query for "the" and compares it to the previous words stored in memory. The pipeline cycles repeatedly, predicting the word "capital," then the word "of," and then Vietnam. This recursion continues until the model predicts a specific stop token, which signals the end of the statistical probability chain and terminates the session. The text appearing on a screen is the result of matrix multiplication and causal looping occurring at a frequency high enough to produce coherent prose. Every sentence is a product of high-speed linear algebra, generating a sequence of tokens that adheres strictly to the statistical patterns of human language.